Archiving started.
Hello and welcome back to the Introduction to Sampling recording sessions. This session will focus in on introducing just the basic ideas behind sampling, and we'll look at some descriptive statistics of samples. A little bit about some of the terminology. So population, total of all possible values, measurements, counts, observations of a particular characteristic for a specific group of objects. So your population could be, oh boy, the number of populations. Student body at SMU. All the students in North America attending four-year universities. All the students attending universities around the world. So you define your population. All households that have one automobile own one car. All households that have internet access in the Dallas-Fort Worth region. Clearly defined boundaries of what the Dallas-Fort Worth region is. That hopefully this gives you an idea. So the population, it's yours to define what it is that you're, which group that you're looking at, a specific group. And I say objects, it could be people, it could be manufacturing items, it could be products. Population, it's a fairly broad concept, but it is what you're focusing your measurement on, and you're going to look at all the possible values that you could draw from. Now, a sample, a part of this population, selected according to some rule or plan. And so we're going to be taking a subset, right? And why do you sample? Population may not exist or is too large to observe all the values. Yeah, we do a national census, but do you want to do that every 2 weeks? I don't think so. There's certain times that you will do a sample simply because it would be too expensive or it's too difficult to go and gather all the data for the full population. Population does not exist. It could be that, certain manufacturing environments, you may not be able to get the entire history of products being manufactured and the yields that were obtained in the manufacturing process. You just don't have that historical data, perhaps, or you're not able to capture it. So you draw a sample. Additionally, why else do you sample? You use the values to elicit information about an unknown population. So you may have a population, and why do you sample? Well, it might be very expensive to go out and ask every single, or do an inquiry about every single entity in your population. Time cost, money cost, resources cost to go gather that information. So you draw a sample. And then hopefully your sample is representative of your population. That's the fundamental assumption here, is that you draw a sample that's representative of your full population and therefore extract that information about that sample and say, okay, this projects onto as a good representation of the full population. Characteristics that distinguish one type of sample from another, the manner in which the sample was obtained, and the purpose for which a sample was obtained. The manner, this is kind of how you structure your sampling, and it goes back to just what I was saying before. How representative is your sample of your true population, and making sure that you have an unbiased sample, so that it is maximizing the representation of your population. Distinguish one type of sample from another. The other is the purpose of the sample. It's a bit cynical, but, pretty much I could make any statement I would want, and I could draw a sample, an opinion. I could have an opinion of any kind, and I believe I could probably draw a sample to support it. If I focus, focus my time on getting the specific sample that I want to draw that supports my opinion. And so that, samples will vary according to that, their objectivity. Types of sample. We'll start with a simple random. Sample x1 through xn is a simple random sample if the x1 through xn are independent, identically distributed, IID, you'll see this quite a lot, random variables. Each value in the population has an equal and independent chance of being included in the sample. Alternatively, say a random experiment that results in a random variable x having PDF f of x is repeated n independent times. And each time you run that, you didn't let x1 through xn denote the random variables associated with these outcomes. And the collection of these random variables, which are IID, independent, identically distributed, is called a random sample. So I like the second note here. Each value in the population has an equal and independent chance of being included in the sample. And in order to have a simple random sample, you have to be very careful in the design of how you collect your information then. So phone surveys, as an example. But would phone surveys be a random sample? Well, think about it right off the block. People that don't have phones don't have an equal chance of being represented in the sample. So, electronic web-based polls, again, equal chance of everyone in your population being able to access and provide. So it's very clear. Maybe your population is the internet-based group of users or people. And so if that's your defined group that's your defined population, it's fine to say you can sample off of that. So a simple random sample sounds fairly straightforward, but you have to be very careful if that is truly what you're going after to design your sampling to actually achieve this. Additional types of sample, stratified random. The population is first subdivided in subpopulations for strata, and a simple random sample is drawn from each strata. So we could stratified random, you could look at subpopulations, freshmen, sophomores, juniors, and seniors. And if you want to have, make sure that your random sample of students at SMU truly represents all of the different students at different stages in their studies, you might stratify it and make sure that you have a poll from the freshmen, make sure you have a poll survey, a sampling from each of those stages, freshman, sophomore, junior, and senior. So that's one way, stratified sampling. Systematic random, the N items in the population are arranged in some order, and then you select an item from the first K, N, again, N is the size of your population, and N is the sample size that you're drawing, so every fifth one. So you somehow are able to order your population. And then if you define your sample size to be 100, you take whatever, whatever number case item thereafter, however, you've defined K, depending on your size of your population. So you might do this, you think about it in terms of if somehow you were ordering all the students at SMU and you draw a sample of 100, I don't know, every 50th student, every 10th student, however you set that up, that would be the systematic random. Empirical distribution function. After a random sample has been drawn, we use the observed sample values, x1 through xn, to elicit information about the unknown distribution. It's a big ticket, right? You draw a sample, you look at some attributes of the sample and say, hey, does this represent the full population? And if we let x of I, what is this also?